All right, so luckily, we're kind of ahead of schedule. So we're getting a late little start here, trying to post an announcement. Be very honest with you. Got a rude reminder, I probably need to get my wedding ring resized because apparently when I was tucking my shirt in, it fell off and I didn't realize until I was about to leave my office. And so then I was in a panic, living in my amygdala, trying to find it. As I moved, I felt something move down my, I was all over my office, going up and down, pulled the trash out. I looked in the garbage disposal of where I was washing some. I didn't feel it like slide down my pants and come out of my pants down here. I was like, it's there the whole time and I didn't know. So that's why I'm a little bit late. Just being honest with you guys, things can happen. Okay. So, we kind of worked through basically all the slides last class of dealing with interaction terms. So we kind of started out looking at dummy interactions. We then kind of moved to thinking about dummy continuous interactions. And then we ended last class thinking about we can interact to continuous variables. Okay. So we're basically going to be kind of rehashing these, just looking at slightly different examples, and we're doing more work in Stata today. So we're going to have these slides. We can kind of go back to them. But really what we're going to be doing is a lot of work with this interaction terms file. And then I put up that additional elections. So if we're looking here, I've got that elections data that we'll work through and that additional do file for election interactions. Okay. We'll be looking at that today. We won't move on to the next topic. I said we might move on to kind of data issues, which will start next week. So what's due at the end of the day tomorrow? Yeah, fourth problem set. So I put up an announcement yesterday, had someone finally come by and was like, what the hell are you doing with question 2A? So in making question 2A, I left out a couple key kind of pieces of information. So I'll actually kind of review that to start class, what I had intended for you to do. But for 2A, basically, everybody's going to get credit as long as you turn in an assignment for problem set 4 for 2A. So I've re-uploaded, oh, not the quiz. I kind of put up what the Word document should have looked like. So if you haven't started it yet, it's not great, but I've kind of updated the file to what I had intended to do with that question. Okay, so we'll do a little bit of review of nonlinear stuff without interactions before we jump into interactions here today. Okay, so and this might be helpful as you're just thinking about working through this problem set. So if I have this regression where I'm trying to predict price with kind of years old of the car, I leave out an important omitted variable, which is what, kilometers driven here. So if I leave out kilometers driven, and after part 1, I've already thought about including kind of a squared term for that years old. Okay. If I tell you the bias that would exist in that years old squared term, you actually know what the coefficient would be of that omitted variable, even without running the regression. So let's think about what this would look like. Okay. So if we're starting out, we're thinking about, we run this regression. And this is where we didn't exactly go through this in class, but given what we've talked about in the past, we should have been able to kind of reason through what this omitted variable bias would have been. So even when I have nonlinear terms that I'm thinking about, when I see the estimate for what that coefficient is on the squared term, it is going to include whatever that true effect should be. But here's where omitted variables sometimes won't really be in, might not be related to the linear aspect of a variable, but they might be related to the nonlinear aspect. Okay. And so here, what would my omitted variable bias be, right? If the variable I left out was kilometers driven, well, you can imagine that's going to be correlated with how old the car is. But that's also going to be correlated with how much someone's willing to pay for that car, the price. So the estimate we come up with on that square term will include the true effect, but it's also going to have, if we had included this important omitted variable, it would include what the effect of that omitted variable would have been on price times what? The covariance of the omitted variable with the variable we're thinking about the bias existing in, which is that squared term. And then we would have this, I would be dividing this by the variance of whatever variable I'm looking at the bias of, which is that squared term. So even without running the regression, if I told you that this bias is negative 0.75, without running the regression to obtain beta 3, how could you tell me what beta 3 actually is going to be? If I'm in Stata, what would I do? Well, if I want the covariance between two variables, I can use that correlate command, put in, what would my two variables be? Kilometers driven, that omitted variable. And how is it correlated with not years old, but years old squared? So this is where I would have had to generate an additional variable, which was years old times years old, or create that years old squared variable. Once I have that, what else do I need? I could use that sum command to find the variance of that squared variable. Once I have those, well, now it's just an equation. I know the bias is negative 0.75. I would know what that covariance is. So I don't know, let's just put some numbers to this. Say this is like let's do negative 2.5. And let's say the variance in years old squared is something like, I don't know, 30. Well, I would just be plugging in what that covariance is, what the variance is. Now I have a pretty easy equation where I could just do some simple algebra to solve for what that coefficient of the omitted variable would have been. So even if I don't have this data on kilometers driven, if someone else did and could tell me the covariance of it with that squared term, I can pick up not only the bias that would exist in linear terms, I can pick up the bias that would exist in the coefficient on the squared term as well. Okay. And, if I had thought about, I could think about the bias of the linear term, but that's going to be slightly different because that's the covariance of the omitted variable with the linear term divided by the variance of the linear term. So we could do this for the squared term as well. This is what I had intended for you to be able to do with that data set, because these are pretty easy commands, at least to the point where we're at now. We can find covariances, we can find variances. I would have to tell you what the value of the bias is, but then it becomes just kind of this simple algebra to back out what the coefficient of that omitted variable would have been without even running the regression. Does this make sense what I'm saying here? Any questions on this idea? So you don't have to do this for the problem set. 2A, everyone will get full credit for this. All right, but this is what you should have been. You now have the updated version of the question, which essentially describes to you what I was just kind of working through. And this is how you would solve for it. Okay. So maybe on an exam, I could give you output of the covariance, these two commands. You could identify the covariance. You could, and actually, sorry, I wrote correlate. What would I need to add here? My covariance on the end. But once I gave you the covariance and I gave you the variance of that variable, which was the squared term of years old, you could back out what the coefficient of that omitted variable was. So using some stuff that we talked about before the exam, just thinking about it now with that nonlinear aspect of the variable we're looking at, or the squared term. Any questions on this idea before we keep moving? So we're going to revisit now interaction terms with continuous variables. Okay, so we'll kind of switch gears a little bit here. So let's look at, well, you know what? I'm running late, so I gave people extra, hopefully people had extra time. Let's go to, before we dive into the data, promised you in class quiz today. So let's go here. I don't know. Today's number will be, got a good one. Because I lost my wedding ring. Oops. Go with the date I got married, right? So 8.17 is going to be today's code. All right, so that should get us into this once I kind of publish it. So 8.17 is the required access code for the day. We'll kind of come down here. I'll get that quiz published. And we'll take a look at the questions that it has. So these should be fairly easy questions that we're going to be looking at today. But I just want to kind of maybe take a step back from what we've been talking about. Okay. So this first question, 8.17 was the code that'll get us into this in-class quiz number 9. So if I'm thinking about this one, I've got select all that apply or multiple answer questions here for this quiz. So if I'm thinking about the interaction, I'll try to stress this, and this might also help on some of the questions that you see on problem set 5. Okay. If I've got the interaction term between two continuous variables or a dummy and a continuous variable. Everybody able to get in that quiz okay? Okay. So which of the following would indicate I should be using that interaction term? So what are two statistics that we want to look at that tell us whether or not the added interaction term has some statistical significance? Easiest would be
The adjusted R squared.
well, I wouldn't think that's the easiest, but that's right? We can't look at the R squared because when we add an interaction term, it's almost like we're adding a variable. What is definitely going to happen to R squared? It has to go up, right? So if instead I can't look at the R squared, what penalizes me for adding in a new variable? But if that variable is significant in explaining the variation in Y, what should also go up? My adjusted R squared. If it goes down, that means that the variable I added, the interaction term, wasn't explaining much more of the variation in Y. So the first thing we want to look at is that adjusted R squared, right? And compare it to the model without the interaction term. So that's going to be kind of one of the things that we would look at. What's the next thing we would want to look at?
The value of the interaction term.
The statistical significance of the interaction term. So we could use technically the test statistic, which would then look at the p-value. We would then compare that to alpha. So that p-value of our interaction term should tell us, right, whether or not that's statistically significant. Now, if I'm thinking about two continuous variables, when I include those, so let's say this was like, might use this later on. So if I'm thinking about, let's say I'm trying to predict quantity and I'm using price. I also want to make a point reviewing some old stuff we talked about with this later on. If I also have the income level of the individual, and I then have price interacted with their income. So I have two continuous variables. The statistical significance of the interaction term, or the p-value, tells me whether or not it should be included. These two linear components, or the original variables themselves that interacted, those may become insignificant. I can have an interaction term that is statistically significant without either of the variables on their own being statistically significant. So the p-values associated with beta 1 and beta 2 here tell me nothing about whether the interaction term should be included. So what would that really mean? If beta 1 and beta 2 are statistically insignificant, but the interaction term is significant, what would that mean? Let's think about what would the marginal effect of price be? Beta 1 plus beta 3 times income. We said when we have two continuous variables and we interact them, the marginal effect of each variable depends on the values of the other variable. If this is significant, but this isn't, what can I technically think of beta 1 as? If it's statistically insignificant, beta 1 is essentially 0, right? What are we failing to reject? We always start out assuming the coefficient is 0. So what that means is price on its own has no influence over quantity. That actually it's price's relationship to what my income is that is driving the marginal effect of price. That the raw kind of baseline effect of price is completely reliant on income, right? Which I think in this is a pretty good example because I mean, prices really don't matter if I don't have any money, right? Or if I have the millions of dollars, the price isn't met, right? The price really is going to be, the marginal effect is pretty much directly driven off of how much income I have, right? Or at least the marginal effect of price is driven. So the statistical significance of the original continuous variables tell us nothing about if the interaction term should be included, right? Only that statistical significance of the interaction term is what we're looking at. So we're thinking about, we look at the p-value of the interaction term, the original continuous variables, those p-values don't tell us anything about whether the interaction should be included. And then the adjusted R squared. The R squared will always be higher. It doesn't tell us anything either. Any questions on that idea? Okay, so I've got this idea of quantity demanded and price down here. And I think about, I want to include an interaction of it with income, right? So which of the following will be true? We kind of already alluded to some of this, but when I'm looking at marginal effects, the marginal effect of price, if this interaction term is statistically significant, will be dependent on the variable I interacted it with, income. What's the marginal effect of income on quantity demanded? Well, that, if I take a derivative, would be what? Beta 2 plus beta 3 times now price. So when I interact two continuous variables, their marginal effect will depend on the variable I interacted them with. So if I think about which of these options are going to be true, the marginal effect of price will depend on the value of quantity demanded. Well, my marginal effect, this interaction term, quantity demanded is my y variable. This one doesn't make any sense at all. Right? The marginal effect of these interaction terms are whatever variable we're looking at, what is its impact on the y variable, but that marginal effect will now depend on whatever variable I interacted it with. So the marginal effect of price will depend on income, and the marginal effect of income will now depend on price. Right? That's what those two marginal effect equations told us. What would the marginal effect of income depending on income actually be? What type of regression would I have where the marginal effect of income depends on what the value of income is? Something we've actually already looked at. So if I had this regression and I'm trying to predict quantity demanded using price, income, but now I include income squared. What is the marginal effect of income now? Beta 2 plus 2 times beta 3 times income. So when does the marginal effect of a variable depend on the value of that variable? Not from an interaction term, but when we have a squared term, right? And it's really like the same thing we're doing with interactions, because technically, when I have a squared term, what could I actually think about that as? Income times income, really just creating an interaction term, but because it's the same variable, my marginal effect looks a little bit different, right? When I take that derivative, I've got this 2 out front as opposed to here. And it no longer depends on the variable I interacted with. I interacted it with itself, right? So when we're thinking about those answers that I kind of gave as distractors here, where the marginal effect of income depends on income and the marginal effect of price depends on price, those would only be true if I was looking at a model that included square terms, okay? So I'm trying to kind of draw a little bit bigger picture and connect kind of what we did last week and a half ago with this kind of previous week and a half. Questions on that? Clear on what the answers are there? You're here. I'll make sure you're getting them correct. So the marginal effect of income will depend on price, and the marginal effect of price will depend on income. Those should be the two answers that we select here. Now here, this is just a freebie, right? There's no right or wrong answer. Any answer you respond with, you'll get the full kind of 2 points basically for being here today. Which of the following you want more practice with? So if we have a little bit of time, if you want to think about more of these quadratic models, so we have the squared term, interaction models, or these models where we're looking at the natural log. In fact, I might kind of revisit those today a little bit as well. Got some time. So just respond whatever you want to see more examples of, and no correct answer to that last question. All right, everybody got that submitted? I'm gonna go in. Oops. What did I have this set to be the end of the day today? So we'll change this now since we got it done. We're at what, 250? I'll put 255 in here just to give us a little bit of leeway on the submission here. Okay. All right. So let's take a look now. We'll look at some more continuous interactions. So I think we worked through all of these last class. We had that kind of happiness, this data we were looking at. So let's look at the election terms file. So I'm going to go back here. If you downloaded that Excel file, we can't simply go to open it. This is where we have to import the data. So I've got this sitting around on my OneDrive, wherever you kind of downloaded this to, because it's an Excel file. Oops, I didn't mean to do that so quickly. Instead of just kind of going to open, we can only open the DTA files. So I've primarily been giving you these already in .dta format. If you ever have a data set you're interested in and it comes in as an Excel, you can always import it. We did a lot more of this at the beginning of the semester, so we're just going to import that election data, right? Our first kind of thing is the variable names, right? So we're going to hit OK. We've now got this election data kind of uploaded to Stata, okay? So I'm going to go here. I'm just going to kind of run some of this code initially. This is just going to scale my variables. So initially I'm going to kind of turn, I think originally the data was in proportions. I want to make it percentages just so it's easier to talk about. So I'm going to just multiply that variable by 100. I'm also going to scale income just to make it easier to think about, because what's the effect of $1? It's going to be relatively small, right? So these coefficients are going to be really small, lots of decimals. I'm just going to scale it by 1,000 so we can kind of work on these interpretations a little bit when we have scaled variables. I'm then going to run this regression where I think this was 2020 election data. I'm going to try to predict, and I think this was county level data. So what percent of the county voted for Trump based off of, I kind of have identifiers for, I think the proportion of that county that was male, different racial identifiers, the total population in that county. But I'm also going to include income and the unemployment rate, right? So in 2020, if we go back a ways, right, we were thinking about, this is when Trump lost, right? So prior to 2020, he was the president. If the unemployment rate was high, do you think people wanted to, in that county, do you think people were more or less likely to vote for him? Less likely, right? But if income was also relatively high, maybe they were more likely. So there might be this interaction between the two, right? Where that even though income is high in that county, if unemployment is also high, maybe there's a different effect of that income. So I included this kind of interaction of these two terms, and we can start to think about, I could use that shorthand. So I run this regression and I look at this and I say, okay, well, each variable on its own, highly statistically significant. Now the interaction term, would this suggest I should be using that in my model or not? The p-value is 0.23. This would be statistically insignificant at our conventional levels. So no. Now, what would I need to run to get the second piece of information of whether the interaction term should be included? I should be comparing my adjusted R squared to when I ran this regression, but without that interaction. So I would want to copy this, paste this, only include income, and only include the linear term of unemployment. So now I'll run these two regressions. And I can see when I didn't include the interaction term, my adjusted R squared was what? 0.4865. My R squared was 0.4879. So what should happen to my R squared when I add the interaction term? It should be higher. Sure enough, 0.4881. It's a little bit higher. But my adjusted R squared, if I had to guess, is it going to go up or down? When we looked at the interaction term, it was statistically insignificant. So likely these two things work in the same direction. They don't always have to be if we're kind of close to that cutoff of a p-value of 0.1. But if the interaction term is statistically insignificant, it's likely the adjusted R squared is going to go down. Okay. So sure enough, I look here, 0.4865, 0.48. Okay. So this is an example where it actually went up a little bit, right? And that's because the p-value wasn't ridiculously like large. It wasn't like 0.8 or 0.9. It was getting closer. I mean, I could say it was statistically significant at the 75% confidence level. So this is where those kind of p-values that aren't really large, maybe the adjusted R squared and the p-value on the interaction term could suggest different things, right? And it kind of just depends on what level would we want to be able to say we should be including this. So this is a good example where even though the interaction term is statistically insignificant at our conventional levels, our adjusted R squared is still a little bit higher. So this would suggest we should be including it. So we're kind of on the cutoff there.
It's comparatively the least significant variable, right?
Yeah.
That's probably a very rare case.
Yeah, I mean, not necessarily. So it actually doesn't matter what it is relative to the other variables, right? Whether or not because the only difference between these two regressions, I have the same variables here. They're all going to have low p-values. The only difference is I've now included that interaction term. So the only adjustment in my R squared is coming from the fact that I've only added this interaction term. Right? So it's directly reliant on just the statistical significance of the interaction term, not relative to the other variables. Because the other variables were in both regressions. Does that make sense? No?
I need to ask you.
Well, no, I mean, this is important. I want to think about this, right? So we're just comparing the model where I didn't include the interaction term to the one where I did include it. Everything else in that regression, exact same controls. So the adjusted R squared will only be picking up the amount of additional variation that interaction term was able to add. So it's not in relation to all the other variables, because if we're making a correct comparison, we should be comparing models that had all the same controls. The only thing that changed was in our second one, we just added that interaction term.
So the addition of this new interaction term does not dilute the average explanatory power of each variable.
Nope. Nope. All right. So we can then start to think about when we find turning points for these marginal effects. Okay. So I'm going to go back to what I said is most often easier for me to do, which is I just like to create the interaction term myself. Excuse me, and run that regression. We should get the exact same results, right? I've just now kind of, instead of relying on the shorthand, I've created this new variable. So what would this marginal effect be? So this is where sometimes writing out what your regression equation is in relationship to your interaction terms is going to be helpful. So if I'm trying to predict percent of people that voted for Trump in these counties, and I'm thinking about, I've got income, I've got unemployment, and I also have the interaction of the two. So what is the marginal effect? Here, what did I do? I said, what's the employment, right? So what would the marginal effect of unemployment be? If I take a derivative of this function in respect to unemployment, what am I left with? Beta 2 plus beta 3 times income. So how would I find my turning point? I'll take that marginal effect and I set it equal to 0, right? So really what I want here, and I could even, instead of using numbers, I could think about this was the coefficient on the unemployment variable. This was the coefficient on the interaction term times that value of income. If I just rearrange this equation a little bit, I'll end up with negative, whatever that coefficient was on the variable I wanted the marginal effect of, divided by a coefficient on the interaction term, will be equal to that income value that represents the turning point for the marginal effect of unemployment. Right? Well, I can grab these from my regression results in theta. Oops. Go. So if I have this regression and I want the turning point for the marginal effect of unemployment, I've got that negative sign out front. I don't want to forget about that, but it's just going to be that coefficient on the variable I'm looking for the turning point or marginal effect of, divided by the coefficient of that interaction term. So if I run this here, this is where I've got to think about, okay, I've got a really, really high value, right? So something really must be going on here. So if I think about, well, maybe I just look at this variable, what was income in? Oh yeah, income was in thousands of dollars. I mean, this is going to be a higher value. So if I think about this income variable that I have, did I scale this? Might have forgot to run the code. Hold on. So let's go back up here. Let's make sure. Oh, I see. So I'm using income here in dollars, right? I didn't use the scaled variable. I'll run the scaled variable here in just a second. So my income looks like the mean was about 50,000. The highest possible income I had on average in a county was 130. These are really rich counties, right? So when I see this turning point is 139,000, will that turning point ever exist? The highest possible county only has an income of 129,000. So will I ever see that marginal effect of unemployment switch over? No, right? It doesn't exist in my data. Okay. So this is where when we're getting questions like this on the next problem set or a quiz, we have to check. We can find that turning point, but to see if it actually exists in the real world, does it fall within the range of that variable, right? When we were solving for this turning point, it was the value of income that represented the turning point. If we don't ever see a county have that high of an income, will we ever see that turning point exist? No. Any questions on that idea? I'm going to redo this just to prove a point to you. If I scale this income variable, what should happen to the statistical significance of those coefficients on, what should happen to the statistical significance of the coefficient on income? Couldn't change at all. The size will change because the coefficient represents the size of the effect of a 1 unit change. But the statistical significance, I'm just scaling that variable, it should be the exact same. So if I go through and try to find this turning point using my new scaled version of income, where it was representing thousands, I should find not 139,000, but if I scale it by 1,000, the turning point I should find would be what? 139.445. So let's go ahead and just kind of see if this is the case, all right? So if instead of income, I'm going to use that scaled income variable that I created up here, okay? I'm then going to also make sure I create this new variable. Actually, instead of me just adding here, I'm going to come down here, create one more. There we go. So I'm going to copy this, paste it. I'm going to create this new interaction term, which was just using that scaled income variable. So I'm going to make sure I change that in my regression as well. And then when I'm using the coefficient, I need to make sure I'm using that scaled interaction that I created. So if I run this code, right, first when I look at these regression results, what do we notice compared to my old regression? The p-values of the interaction term and income, so the test statistic was -10 and 1.19, exactly the same. Didn't change my statistical significance at all. Now, what happened to the size of the coefficient on income and the size of the coefficient on the interaction term? They're now quite a bit larger. Why? Because before, when I had the income variable, that represented the effect on the percent of people voting for Trump from a $1 increase. It now represents the percent increase in the people who voted for Trump from a $1,000 increase. So it changes the size of my coefficients, but not the statistical significance. Okay. So what it should do is scale both that regular income and the interaction term by the same amount. So that if I use my new regression and find my new turning point, I find that exact same value, but it's now in terms of the units that I made that income variable in, which is in thousands. So instead of 139,000, I find 139. So we can still use scaled variables to calculate these turning points. We just have to think a little bit harder about what they represent, right? It doesn't represent an income of $139 on average in a county. It represents the average income in a county would have to be 139,000, whatever that new scaled variable is in, whatever its units is. Okay. Any questions on this idea? Early on time. Okay. So I wanted to kind of show you, if we go back and we don't use that scaled version, I'm just going to copy and paste this here. We could do the exact same thing. I think we've probably seen enough examples where it's not crazy important here. But notice if I want the turning point for instead of the marginal effect of unemployment, but the marginal effect of income, the marginal effect of income, if I've interacted it with unemployment, should depend on the value of unemployment. So instead, it won't be the coefficient, right? So here I had the turning point of unemployment was the coefficient of unemployment divided by the interaction term, and there was a negative sign out front. When I want the marginal effect of income, right? That'll be the coefficient on income divided by that interaction term. So I could do the exact same thing and find the turning point, for unemployment, right? Remember, this is going to be, if I want the marginal effect now instead of unemployment, that would be equal to beta 2 plus beta 3 times what am I wanting here? We already did that. We're looking at the marginal effect of income now. So that would be what? Beta 1 plus beta 3 times unemployment. So I'm now going to have the marginal effect of income depends on unemployment. So this turning point I find is the unemployment rate at which having an additional dollar increase in the average income in that county would actually have a marginal effect that is negative. How high would unemployment have to be? Well, if it's in terms of percentages here, we found the turning point is actually 54,000, right? Or sorry, 54,000, 54%. I'm going to go out on a limb. We probably don't even need to run this sum command. But if I look at the range of unemployment, what's the highest it can be? I mean, 100, but like the highest unemployment, I don't even know what county this is. It's wild that probably Appalachia, somewhere in West Virginia, that it's 28%. So are we ever going to actually see that turning point exist? Not even close for this marginal effect, right? So this is where, even though we can find these turning points, we want to check to see, will they actually exist in the real world? And we can use the data to look at, okay, what's the range of that variable? If that turning point isn't within the range of our variable, we know it'll never exist. Okay. Now, theoretically, technically, it could exist because technically unemployment could be 100%, but we don't actually see that with our real world data. Any questions on that idea before we keep moving? Okay. So I had this additional line in here. This might be something I wouldn't push you guys probably this far, but just if you're interested. So why might you not want to use this method where you create your own interaction term? I think I showed this before when we were looking at the squared term and nonlinear relationships. But if I interact two continuous variables, I can also run this command in Stata that will tell me, well, technically, when we had dummy variables interacting with continuous variables, I said last class, we would have a marginal effect for the 0 group and a marginal effect for the 1 group. Here, the marginal effect of income would be different for every single possible unemployment value I could see. So if I wanted to calculate this, I could technically calculate an infinite number of marginal effects, right? So what we're going to do is in Stata, you can run kind of that shorthand without creating the variable yourself. And then it says, I want to predict the marginal effect of of income. So this dy dx, this is what you're taking the derivative of y in respect to, right? The x variable. So I want to know the marginal effect of income. Well, if I've interacted it with unemployment, I know the marginal effect of income depends on the level of unemployment. So what levels do I want to predict the marginal effect for? The marginal effect of income for unemployment rates from 1 up to 75 in 1%, 1 unit increments. So essentially, I want to find the marginal effect of unemployment is 1%. I want to find the marginal effect of income when it's 2%. Marginal effect of income for 3, 4, all the way up to 75. Just so we don't have a crazy number, let's just do 25 so I don't get too many values to look at here. So I could run that kind of margins command. And what I'll see is, nope, because I actually have to run this regression first, right? So I have to run this regression. So maybe this is a good point. When I ran it using my variable that I created, it doesn't identify that interaction term. So if I don't have an interaction term, the marginal effect should just be linear or always the same value, right? So I actually need to run my regression that included that interaction term, right? So when I run this and then run the margins command, now I see, the marginal effect starts out as negative for income, but as unemployment goes up, that marginal effect of income actually gets lower and lower and lower. So this one's kind of a weird result, but basically the effect of counties becoming more wealthy when Trump was president actually made them less likely to vote for him in the following election. Income is highly correlated with political affiliation. So there's some weird things going on there with incomes probably picking up the omitted variable bias of a lot of other attributes, right? We don't have a ton of controls here, but that's how we would kind of interpret this data, right? I always think this is a funny example too, because what's happening to the marginal effect of income as unemployment is higher, it's going down. So when these counties had more income, even though unemployment was higher, having more money actually made it like more likely they were going to vote for Trump, even though unemployment was higher. So this is like, once again, maybe this is my bias showing itself, but this is me thinking about like some good old boy in West Virginia being like, to hell with it. Who cares if, income is going on, right? They ignore the current unemployment situation. The fact that they have just a little bit more money is still creating kind of a smaller negative effect. So you could kind of do this for other things as well. So let's say I ran that same regression. I could use the margins command to say, okay, I want to know what the marginal effect of unemployment is, but for different values of income. So here I said from 50 to 150,000, and I did jumps of 10,000 just to kind of make it so there's fewer results to look at. So I could also look at the marginal effect of unemployment for different values of income. Now here's where it kind of is unfortunate, the way in which Stata does this. It doesn't give me the actual values. It just kind of says like 1 to whatever. So wherever I started, that would be the marginal effect of unemployment at 50,000. Marginal effect at 60,000, so on and so forth. So what was happening to the marginal effect of unemployment? Well, as unemployment went up by 1 unit, the effect on whether or not there was an increase in the percent of people that voted for Trump, it was becoming a smaller value as income went higher. And then eventually there was this turning point, which sure enough was right around that 139,000 that we found earlier. Now, I won't push you guys as far to kind of produce these margin results, but you can do this. And this is how you could find the marginal effect at really any range of values. And then you could use this, maybe a more like data visualization class. We could create some nice kind of graphs of what is happening to that marginal effect. All right. Any questions over anything here before we keep moving?
So earlier you mentioned a hypothetical where the individual variables aren't statistically significant, but the interaction term is. Is there a situation where you would want that interaction term, but not the individual variables?
So technically, I'll say this in a way that's maybe not quite correct, but if I have an interaction term, I have to include the linear component of that variable, right? Because if I don't, my interaction term starts to pick up the omitted variable bias of just what the baseline of that was. So even if it isn't statistically significant, I still need to include that variable in my regression. Right? If I don't, without going too off the rail, so let's say I had income and unemployment, and I just included unemployment and then the interaction of income and unemployment. I leave every value of income. When I multiply, I might run into some like collinearity issues. But when I control for income and unemployment, now my interaction term, I won't run into any of those multicollinearity issues. So anytime you have an interaction between two variables, you need to have each of those variables in your regression as well, even if they're statistically insignificant. Okay? Like I said, a little bit outside the scope of this class, but you're thinking about it the right way. Like if they're not significant, why are we including them? Well, it gets into issues of multicollinearity. And that's why if we have an interaction term, we have to include both those variables as well. Any other questions? Anything here? So I think we looked at like this children's hours work stuff kind of last class. So I did a pretty good amount of work with this interactions, continuous. I kind of worked with the elections file here just to kind of give you a little bit of different taste of things, just a different example. After class today, I've got the 5th problem set ready to go. So that 5th problem set will just only be about interaction terms. So both of these do files you can use. I'll post that up. I think I've got the due date set to be quite a ways off. So I think I have it not to be next week, but actually that following Wednesday. So almost 2 weeks to work on it. Oh, where is it? I haven't put it under the module yet. There it is. So November 19th. So you've got, just under 2 weeks to work on this. I would suggest working on it sooner rather than later so you don't get too far removed from actually covering the material in class. I realize that 4th problem set isn't due the end of this week, which is why I gave a little bit more time on this one. All right. So if you're still finishing up that problem set 4, make sure you do that first. But then after class today, you'll have that 5th problem set that's just talking about interaction terms to start working on. Now the quiz, I kind of have quiz 5 ready to go. It's not currently on the Canvas course. I've got a template course that I have. It includes some material about what we're going to begin next week with, which is data issues. And so that quiz, that won't be posted until next week. So we're going to have a little bit more time until the next quiz because we have to cover those data issues materials next Tuesday and Thursday. But that'll be kind of due that end of that week right before Thanksgiving break. Right? So just kind of thinking about where we're going. So this past subject, the quiz was due before the problem set. On this next set, the problem set will only include interaction terms, but the quiz will include interaction terms plus these data issues, additional data issues that we talked about. So they've kind of flip-flopped there. Questions you have just in general about interaction terms, anything we talked about the last about 3 class periods now, today and the previous 2? Or what if something looked like this, or yeah.
I'm still a little confused on the adjusted R squared, like the problem that we did where the adjusted R squared was higher.
Yep.
Even though the p-value wasn't statistically significant.
Yeah, so why can these work in the opposite direction? Is that kind of what you're getting at? Like, why would the p-value suggest I shouldn't be including the interaction term, but the adjusted R squared suggests I should be?
Yeah, and like what to do in that situation, like to.
So basically, if I have a question, like once you see that problem set posted, because there might be a question that looks like that, I just want you to indicate what both of those would suggest. They might not line up. If they don't line up, just like in a lot of other econ courses, the answer is take like a basic econ. You have supply and demand simultaneous shifts. Sometimes the answer is not determined, indeterminate, you can't determine, ambiguous. When we run into those situations, we've got some evidence that suggests it should be, some that it's not. Can't really determine, right? And that's because like you kind of technically can determine it, but like that p-value of 0.23, once again, it doesn't meet our conventional levels. And this is where if you're looking at research, it's a little bit kind of outside this class, but like if you were to kind of continue, you're thinking about doing your own research or you're looking out there at academic papers, they will sometimes report things. And even though they don't find statistical significance, like just because the p-value isn't below 0.1, is a p-value of 0.12, should I just be like ignoring that? I mean, it's significant at the 88% level, right? So it's like, just because we don't meet these like high levels, which are kind of like the academic rigor levels, 0.25, like I said, I could really say, I think it was just below 0.25. So I could say that it was significant even using the p-value at the 75% confidence level. There's a lot of things in life I wish I could say with 75% confidence, right? So just because they don't meet our conventional levels, just because they aren't statistically significant at the 90, 95, and 99, doesn't mean we should be completely ignoring them. In fact, if I was doing this research on my own, I was writing the paper, I would write out that yes, our interaction term is not statistically significant at our conventional levels, but it is at the 75% confidence level, and the adjusted R squared went up, suggesting it should be included. Now, if I start to say that when my p-value is 0.8, well, saying that with 20%, in fact, if the p-value was 0.8, it's very, very unlikely the adjusted R squared. There probably is a threshold depending on the number of observations where you can actually say whether or not those two things will go in opposite directions, right? For most data sets that we have, anything of adequate size, if you start to get p-values that are below 0.5, your adjusted R squared is also going to be going up. Or sorry, your adjusted R squared is also going to be going down, right? If your p-value was like 0.5, 6. But it's these kind of ranges where it's like, it doesn't meet our high level of statistical significance, but it's not completely statistically insignificant. Those are situations where you can see that p-value and the adjusted R squared may be suggesting different things. Is that?
Yeah, thank you.
I have a follow-up on that. I understand the rule. But what is actually in the data that forces that change? Is that
In the adjusted R squared?
yeah.
So we would go back. We have an equation for the adjusted R squared, right? So it's 1 minus, what do we want? The proportion that you can't explain, scaled by this factor of what? N minus 1 over N minus K minus 1, right? So that's why I said there is going to be something like, it's related to the number of observations we have about whether or not we can see these conflicting results and how much variation that it still leaves unexplained. So it's, if I reread, it's going to be some function of how much that additional interaction term reduced the proportion we can explain. Now, we always know this is going to go what? By adding a new variable, the proportion I can't explain is always going to go down, which that's our R squared, right? So 1 minus a lower value, our R squared always has to go up. It's something about how much more variation can we explain relative to that ratio of the observations to the number of variables that we included that is going to say whether or not that adjusted R squared actually could go up or go down, right? Vice versa. So, I mean, this is very I'm not going to ask you guys about this, right? This would be pretty tricky, right? Because then I could give you, if the number of observations was 50, you have 6 control variables. What would the proportion and variation explained have to go up by in order for you to actually find a higher adjusted R squared? You could do that. It's just pretty hard. I mean, it's a lot more difficult than me just asking you about the directional changes and what that suggests, right?
What p-value or test statistics would be associated with that turning point where it switches, where the effect switches?
Once again, I have no idea. It's going to be some function of the statistical significance of the interaction term, or how much it was reducing the proportion we couldn't explain relative to both the sample size and the number of control variables we added. It's going to be some function of those 3 things, right? But once again, I don't think you want me to ask you those questions, so that'd be a lot harder. Right? Any other questions on this idea? It's a good question though. Like it seems weird. Right? Other questions that we have on anything with interaction terms. So I've got something else I kind of want to work through. So how many of you are still enrolled or are going to be enrolled in economics courses this semester, next semester? Most everybody, right? If you're not, apologize, you probably have taken other economic courses before this. So one thing that we've kind of shied away from, or we haven't really touched on, and we still could use them, but I'm not going to in this class, right? Is you could start to look at interaction terms. What can I do with a continuous variable? What type of model could I run? Not just a linear model, but a linear or a log, right? So if we start to think about what are these log, I could use interaction terms there. We're not going to, because the interpretation becomes a lot more difficult, right? But I want to kind of revisit those just to kind of relate it to what your other econ courses are talking about. Especially, have you guys all taken the, I don't know that I'm still learning numbers here, but the intermediate micro, has everybody pretty much taken that? So if I'm thinking about, if I take the natural log, quantity demanded, and I run a regression, I can go out and get some data on whatever product this is, and I use the natural log of price. But let's also assume, I'm going to add in there one other thing, which I'm going to take the natural log of income. What's the interpretation of beta 1? If this is a log model, the interpretation would be a what? A 1% increase in price results in a beta 1%. And here I can't say it's an increase or decrease. I should have said change, right? But we kind of know the relationship between price and quantity demanded if we know anything about our demand curve, right? So it's a 1% change in price will result in a whatever beta 1% change is in quantity demanded. What does that look similar to? What is this? The elasticity of demand. So when you have these like introductory courses or intermediate where you're talking about elasticity of demand, sometimes they'll actually show you what the estimated values are for different products, right? Where do those values come from? Log regression. Now, let's say I told you, I can actually estimate what beta 1 is, right? So I can kind of think about beta 1 is really representing to me the elasticity price. So if that beta 1 is less than, so I shouldn't say less than, an absolute value, less than 1, what type of good do I have? This is going back to like, I guess, intro micro. But if my elasticity is less than 1, that good is inelastic. That's how we identify if goods are elastic or inelastic, is from a log regression of price and quantity demanded. Now, we would like to control for a lot of other factors when we're estimating these relationships, but notice what can I also do here? What is the interpretation of beta 2? A 1% change in income would cause a beta 2% change in quantity demanded. What is the percentage change in quantity demanded coming from a percentage change in income? My elasticity of income. This tells me if it's a normal or inferior good. Or these other categories we can kind of break these down into. So in a lot of your other econ courses, when you're talking about these different values, where do these values come from? Regressions. And in fact, when we're thinking about percentage changes or elasticities, which we often are looking at in economics, all we're doing is we're running these log models. Okay. So I don't know. I teach the intro micro, so these things are always in the back of my mind. But I do want to try to like give you guys bigger pictures. I think today was a lot more bigger picture, trying to connect kind of things between the interaction terms, the squared models, but also these kind of nonlinear models as well, how that connects to some of the other econ courses that you're looking at. Okay. So if you're ever interested in elasticities, you should be using log models. Okay. Questions on this idea? All right. So I'll get that kind of 5th problem set added up here on Canvas. Next week we'll start. It's going to be a little bit weird because the variety of topics we're going to be talking about is not as quite, there's more variance, right? We're gonna kind of look at very different data issues. So next week, it'll seem like we're looking at a lot of different topics. And we'll try to relate them to things that we've already talked about, but it won't be as like narrowed in as it was when we were looking at nonlinear relationships with like squared and natural log. And it won't be as narrowed in as when we're just looking at interaction terms. It's gonna be a little bit more broad. Okay, so we'll kind of start with that next week. Other than that, sorry for the late start to class today. But you're getting out of here early too, so we'll have a fun, safe weekend. I will see you guys on Tuesday. Yep.